Hi dear participants, welcome to the 5-day online workshop. So in this video I am going to tell about principal component analysis, and we will use one uh, example to solve these solving these principal components and using SPSS software. Okay, so I am Amaresh, assistant professor. So the principal component analysis is a statistical procedure that uses an orthogonal transformation to convert a set of variables of possibly correlated variables into set of linearly uncorrelated variables. Okay, so these linearly uncorrelated variables are called principal components. Okay, so in the original data set we have correlated variables. So these correlated variables are transferred into new set of linearly uncorrelated variables. So these linearly uncorrelated variables are principal components. Okay, so the new variables are linear combinations of original variables and are derived in decreasing order of importance, so that the first principal component accounts for the maximum variability as in original data. So next is the main features of PCA. So the PCA is a variable reduction method or data reduction method, or it can also be called as a data dimension reduction method. Okay, so here we will reduce the number of variables to few factors. Okay, so the few principal components, and so used when the variables are highly correlated. It means when we are studying the variables are under study has should have the correlation. Okay, so these the variables should have some correlation among themselves. So then it is the PCS course will result in precise analysis. Okay, so the next the first few principal components accounts for most of the variability in the original data. It means the first few components means PC 1, 2 or 3 will explains the is more than 70 to 80% of variation in the original data is explained by first few principal components. Okay, so it is a statistical technique which does not require user to specify the statistical model or assumptions about distribution of original variable. It means in case of regression or in univariate analysis, the regression and other techniques require some model assumptions like the population, where the variables, the population should distributed with normal, and error should be distributed like this. Okay, so like that the in PCA we don't have such assumptions about distribution or model assumptions. Okay, so next is the principal components or artificial variables. It is not possible to assign physical meaning to them. Okay, so next this is the mathematical structure of the PCA components. Okay, so these are in this we have a q original variables, and then the principal components are defined like this. The P1 is equal to a11 x1 plus a12 x2, so on a1q xq. Okay, so these P1, P2, P3, PQ are principal components. Okay, so these are the principal components. So this is as I already told you, it's a linear combination of original variables. It means these principal components are linear, so these x1, x2, x3, so on xq. Okay, so these the original variables are in all the principal components. Okay, so it means it is a linear combinations of original variables, and in this equation we can see these linear these are all the coefficients which are attached to the original variables. Okay, so these coefficients are called aij. These are all the factor loadings or component loadings. Okay, so these are attached to these coefficients are such that the sum of squares of these coefficients should be 1. Okay, so and then next is the principal components are uncorrelated. Okay, so they are orthogonal to each other. Okay, so these P1, P2, so on PQ principal components are orthogonal to each other. Okay, so next is PCA involves the finding eigenvalues lambda j's. Okay, so these lambda j runs from 1 to q. So eigenvalues of this matrix. Okay, so variance covariance matrix, it is denoted by this sigma. So the eigenvalues of the matrix are variances of principal components. Okay, so the eigenvalues are variances of these PCAs and can be found by solving the characteristic equation. This is the characteristic equation. Next is PCs depend on unit of measurement, so standardize the variables with zero means and unit variance. It means when we have a more number of variables which are measured in different units, so we have to standardize these variables and then start the analysis. When we standardized these covariance matrix, takes the form of correlation matrix. Okay, so this is the script plot. Okay, so this there is always a question of how many principal components to retain in the analysis. Okay, so this question is answered by this script plot. Okay, so script plot is the plot of eigenvalues versus its components. Okay, so the principal components here in the y-axis we will take eigenvalues, and in the x-axis we will take principal component number. Okay, so this is the p1, p2, so on. Okay, so the point where the slope of a curve is clearly leveling off. Okay, so in this graph in the PC2, okay, so in the principal second component we have a leveling off, or the elbow shaped indication, which means the first two principal components. Okay, so these two principal components should retain in the analysis, and these two principal component will explain the maximum amount of variation in the original data. So let us take one example, and so I have a data on genotypes. So the genotypes are measured with different variables as a flower. So you can see we have 11 variables here. So these 11 variables are: x1 is number of days for flowering, number of maturity, a plant height, branch. Okay, so like this we have the 11 variables. Okay, so our aim is to find what are the main factors among these variables, which factors are very responsible for genotypes. Okay, so which factor is more important? Okay, which factor has the more weightage on the performance of the genotype, or a genotype. And second is we have to reduce this data set with a few number of variables. We will do that using the principal component analysis. Okay, so I will use the SPSS software. So I am using 20 version here. I will copy this extra data. I will paste into this sheet, and in the SPSS we have data view and a variable view. Okay, so we can edit the variables. Okay, so we have x1, this is x1, and x2, x3, x4, x5, x6, x7, x8, x9, x11. Okay, so we have these 11 variables, and we have, okay, so these are all the 11 variables. So then we have to go to analyze and data reduction and factor. Okay, so select all, control A, and drop these variables into variable box. Okay, so then click on descriptive, check the enumerate descriptives, and in the correlation matrix select these two significant levels and coefficients and continue. So in the extraction by default it is a principal component method. We have to use this for principal components and select the correlation matrix. Okay, it will if we select this, the correlation matrix, the eigenvalues are determined using this correlation matrix. Okay, so then check it, scree plot. Okay, so we have to extract the eigenvalues which are greater than 1. Okay, so then continue and click OK. So this is the result or output of the SPSS software. We have to see first descriptive. Okay, so in the descriptive we have mean, standard deviation, and how many number of observations in these each variables. Okay, so this is the for x1 it is the mean and standard deviation, and in x1 we have 64 observations. Okay, so like that it gives the descriptives of each variables. Okay, so then this is the correlation matrix. Okay, so we have to see the among these variables, we have to have a the significance correlation. That means we want the most positive or a most we want to have high correlation. Okay, so as you can see, this is the p values, this is the significant level. We have to compare these p values with alpha, that is level of significance. Okay, so level of significance, it may 1% or 5%. Okay, so the values which are less than 0.05 are significant. Okay, so this is significant, and this is also significant, and see, this is significant, and these are all the significant. It means these are all the significant values, the respective correlation values. These are all the respective correlation. This is the R values. Okay, so we have a high correlation in this the among the variables. Then our we have to go for the PCA. Okay, so next is the total variance explained. Okay, so this is the eigenvalues and the percentage of variation explained by each eigenvalues, and this is the cumulative percentage. We can see the first eigenvalue is 4.1 and second is 2.45, and the first eigenvalue explains the 37.273 percentage of variation, and second eigenvalue will explain 22.34 percentage of variation in the original data. And when we look the cumulative, the first four eigenvalues will explain more than 80%. Okay, so 80.116% of variation is explained by explained by the first four principal components. That's good. Okay, so then when you see the scree plot, we have a elbow shape or a bend in the first four principal components. It will explain the maximum amount of variation, so we have to retain the first four the principal components. Okay, so this is the component matrix. Okay, so this matrix will tells the importance of the each variable in the first principal component and second principal component. Like that, we have to look for the maximum, the most positive value here. The we can see this is among this we have a x5, that is 0.92. So this is very important or major factor which will contribute for determination of good genotype. Okay, so we can sort this component matrix so that we will have a clear picture. Okay, so we will sort that and go to analyze and dimension reduction and factor. So in this for that we have to go for options, and in the coefficient display matrix, sort by size and suppress the small coefficients which are less than 5. Okay, so we will suppress these values and sort by its size. Okay, so then click OK. So these are all the in last week. So, okay, so this is the sorted component matrix, which shows I will compare these values with these variables here. Okay, So okay, so you can see the x5, that is x5. What is x5? Is number of pods per plant. Okay, so this factor influences the more. Okay, so this factor got more weightage in first principle component, and second second factor is point x9. Okay, so x, what is x9? Seed yield. Okay, so these the indicator or this factor will contribute more. Okay, the first factor is number of pods per length, and second factor is seed yield, and third is extend the harvest index, and fourth is x8 biological yield, and x7 is number of seeds per plot. Okay, so this is sorted by according to its weight. Okay, so in the first principal components, okay, these are all the indicators, or these are all the factors which have to be, which are got the more weightage. In the second component, x1, x2 and x6 got more weightage. Okay, so x1 is number of days for flowering, and x2 is number of days to maturity, and x6 got the most negative weightage. Okay, so you can see here minus 0.70. Okay, so it has a negative weightage in second principal component. Okay, so like that, so the first question is answered here. It means the main factors which are responsible for measuring good genotype. Okay, so these are all the factors which are responsible for the good genotype. Among these factors, these the most weighted indicators have shows the main factors. Okay, so these are all the main factors. Okay, so next uh, we will calculate the extracted principal component scores. Okay, so for that we need this component matrix. Okay, so for that we need these eigenvalues. First I will copy this. Since we have extracted four components, I will use these. Okay, so here see, we have four components are extracted. That's why I have taken that four components, and I will use these. Okay, so these are all eigenvalues. Okay, so these are all the components. I'm going to calculate. These are all EIJ, that is component loadings. Okay, so I will calculate the component loadings. Component loadings are calculated by this. Okay, so we have to take the first principal component score and divided by square root of first eigenvalue. Okay, so this is how we have to calculate. Okay, so this is the factor loading. Okay, so these are all the first factor loadings, and so second loadings are calculated similarly like that. Okay, so score divided by square root of second principal component or second eigenvalue. Okay, so then click OK. So this is the second like that we have to calculate this, and square root of third eigenvalue. Okay, so the score of fourth factor, and then square root of fourth eigenvalue. Okay, so these are all the eigenvalues, and Okay, so then we have to, for that we have to standardize these original variables. Okay, so I have standardized here using these standardized syntax. Okay, so for that we have to use this. So we have to calculate mean for all the each variables and standard deviation. In this way we have to standardize these variables. Okay, so after standardization we will have, so now we will calculate first P3 and P4. Okay, so these are all the principal component scores. Okay, so we have to select 64. Okay, since we have a 64 variables, we have to select the 64 range, and in then is equal to m mult. Okay, so this is matrix multiplication. We have to select the standardized variables. These are all the standardized variables, and then comma, we have to select the component first principal component loadings. Okay, so this is the first principal component loadings. Okay, so I will fix the standardized variables. Then we have to control shift enter. Okay, so these are all the first principal scores, and when we drag this, okay, so we will get okay, so these are all the first four principal components. Okay, so and this is the, we will calculate variance of the PCs. Just to check. Okay, we can, that's good. So these are all the first four, these are all the PCA scores. Okay, we can see that I have told you. So this is the equation. So in the for better, so these are all the component loadings. Okay, so these are all Aij. Okay, so Aij, these are all the coefficients. Okay, Aij. Okay, and so this the first PC1. So this is the equation of first PC1. It contains the factor loadings along with original or standardized values. Okay, so for calculating this we have used, these are the compound loadings and the standardized values. Okay, so this is the first principal component. So this is second principal component. This third, and this is fourth principal component. And I have also told you the eigenvalues of the matrix or variances of principal components. Okay, so the variances of principal components. Okay, we have calculated the variance of these principal components, that comes to, okay, so the variances of first principal component is 4.1. okay, so this is, we can see the eigenvalue of first principal component is 4.1 and variance of first principal component is 4.1. Second eigenvalue of second principal component, the second eigenvalue of second eigenvalue is 2.458 and variance is also 2.58. okay, so we have also verified this. Okay, so this is how the, okay, next so in the original we have x11. okay, so these original x11. okay, so we start with x11 variables, then by the end of the process we have a smaller variables. okay, so the smaller variables means the x4 variables are extracted, which these, so still these will reflect a large proportion of information contained in the original data. okay, so how much percentage of that will explain. okay, so as we can see here, the first four components will explain, 80% of variation in the original data. And also we have seen that by component matrix, what are the factors or which are responsive, which are most weighted in the uh, analysis. Okay, so I have also explained this. Okay, so this is how the principal component will be used in the this type of analysis. Okay, so the principal components are these. Okay, so these principal components, okay, so these principal components further analyzed or used in different analysis to get good results. Like where can be used these principal components? It means when in the regressor, in the regression, we have a collinearity problem. We can use these PCs to come back to reduce the multicollinearity and better R square and better result of in the regression. And so these PCAs can also be used for construction of what are the composite indexes. Okay, so these are all the uses of the principal component analysis. And I hope I have explained you the PCAs in very clear. And uh, uh, thank you. Thank you.